to start again. Okay. Here we go. And we need 3 rows. And this is going to be I, the initial. This is C, the change. And this is equilibrium. So we have the initial concentrations. We're going to write them in. So CO was 0.27 molar, 0.27. And H2 was 0.49 molar. And they're not saying anything about the product. What's the product concentration usually at the beginning of a reaction? It's 0. Because that's what you're making, and the way you're making it is putting the reactants together, so you don't have any of it to start with. So when it just doesn't say anything about the product, that's 0. Okay, so this is the equilibrium concentration of the product, so that's 0.11. And now we want to look at how these things are going to change, and it's related to the stoichiometry of the balanced chemical equation. So anything with a coefficient of 1 will change by X. This is a reactant. It's going to decrease by X. This product is going to increase by X. And what about this guy? Minus 2X. Half right. Because it's a reactant. Okay. It's going to decrease. So now we know that 0 plus X is equal to 0.11, which tells me that X equals 0.11. So over here then, this is 0.27 minus 0.11, which will be 0.16. Yes? And this will be minus 2 times 0.11, which I think will be 0.27. Yeah. Dangerous doing math like that in your head. Does that make sense? How do we find the equilibrium constant? We write the expression and plug in the equilibrium concentrations. Kc is equal to the concentration of the product divided by the concentration of the first reactant and the second reactant. So 0.11 divided by 0.16 times 0.27. There we got another one of those divided by 2 things. So do this on your calculator and make sure that your calculator is understanding what you want it to do.
Wouldn't it be 27 squared?
Yes, it is 27 squared. Thank you. I got 9.43. No, it says 9.4307. And so it's like after the 3, there's a 0, so the rest of the stuff just doesn't matter at all. Does it hurt anything to keep that 3? No, it doesn't hurt at all. Any questions? So we are going to use variations of this in the rest of this chapter and in the next chapter. And so it's really, really important to understand how an ice table works. 9.4. Here's another one. Reaction shown is carried out with initial concentration of .087 for the reactant. And at equilibrium, they give us one of the product concentrations, find the equilibrium constant. So I've got my initial concentrations, how they're changing, and my equilibrium. So this was 0.87. What are the concentrations of the products? Well, not the change, but the concentrations. To start with, they're 0. And then I'm told that H2 is 0.012. So this is one that has a coefficient of 1. So we're going to call that change X. And so this is going to increase or decrease in concentration? It's going to increase. It can't go lower than 0. So this is going to be plus X. And this one is going to be what? Plus 3X. And this one is minus 2X. Isn't that convenient? So whichever one that we have all the information for, that's how we figure out what X is, because the equilibrium concentration has to be the initial plus the change. So, you know, if you want to write those in the boxes, you can do that. So this would be plus 0.004. Or if you just want to look at it, okay, it's this plus X, that's X, and so this must be 0.004. This is minus 2 times that. So 0.87 minus 2 times 0.004, 0.862. Now, we do not want to get silly about sig figs here, because technically subtracting this or adding that, that's often past the sig figs, right? So do we just say, well, it's 0? No, because it is something. So we're going to be kind of reasonable here. So now we can do our equilibrium constant expression. So Kc equals C2H2 times H2 cubed divided by CH4 squared. So we've got 0.004 times 0.012 cubed divided by 0.862 squared. Mm-hmm.
0.087. For the CH.
Oh, thank you. Yeah, that'll mess things up. So I lost a 0 there. That's not good. Thank you for catching that. 0.087, so I need to fix this guy. Okay. So 0.079, is that better? So on these problems, avoid the temptation to try to do it in your head. I wouldn't if I cared to get the answer right. It's just too easy to mess up. It doesn't take that long to just write this down, and then if something goes funny, you can look and see what you did and figure out what happened. Maybe you just punched it into your calculator wrong. So I'm getting KC equal to 1.1 times 10 to the minus 6. Is that an okay number for an equilibrium constant? Sure. The only requirement is that they're positive numbers. They can be mind-bogglingly huge or infinitesimally small. Any questions?